So you'll remember in our early introduction to magnetostatics, we studied a force law and we wrote down the Biot-Savart law. And although I didn't prove that the curl of B, or pardon me, the divergence of B was zero, I did suggest how you would go about proving this fact. And because the divergence of B is zero, we know that we can always write B as the curl of some other vector function. In this case, we call it the vector potential A. Okay, so what we're going to do in the next lecture, or pardon me, in this segment, is we're going to develop an equation, or actually I'm going to write down an equation for the vector potential A, and then we're going to revisit our current loop problem. We're going to calculate A first, the vector potential, and then we're going to recalculate B by taking the curl of A. And of course we should get exactly the same result that we obtained earlier, but we have to be somewhat careful about this calculation, as you'll see. So it's actually a very instructive calculation to follow. Before I do write that down that equation, I'd encourage you to actually go and prove that for any curl, if I were to take the divergence of the curl of any vector field which is differentiable, let's call that field, let's call it A for the time being, that this is always zero. So it might be useful for you just to have a go at proving that, just to convince yourself that this is always the case. Okay, so again, I'm going to avoid a detailed proof of the formula for the vector potential for A, and I'm just going to write it down. Okay, so this is the equation we're going to use, the expression for A. If you want to have a look at the proof for this, again, go and have a look at it in Griffith's or any other classic textbook. It's not a very instructive proof, so I'm going to concentrate more on using this formula rather than proving this formula, but please go and look it up if you just to satisfy yourself. So if we want to calculate the vector potential A at a position R, due to a current element J at R prime, let me just clean up my vector symbols here, a current density element, J at R prime, then this is the equation that we would use. Having obtained the equation for A, we can then calculate B by taking the curl of the A field, and this is going to be the subject of this segment. So we're going to return to our current loop problem and calculate the vector potential and then the magnetic field. Okay, so this is our old problem, the one that we studied before. Here is our current loop. It's of radius R. And we put the current loop in the xy plane. We're interested in the magnetic field at this point, or in the first case we're interested in the vector potential at this point here, a distance z hat above the center. Okay, now you might be tempted to think that we only need to calculate the vector potential at this point here, and then we can take its curl. Well, let's just have a quick look at this. This is wrong, but let's have a quick look at this anyway. If we calculate the vector potential here, or actually anywhere along this axis, what we will get is we'll in fact get zero. You'll find that the vector potential is zero everywhere along here. So it's not just that it's zero, it is a constant. And if I were to take the derivative of a constant, I would get zero magnetic field. So if I were to try and take the curl of a constant, I'll get zero. Well, this is a problem. And the issue here is that in order to calculate the magnetic field from A, we're going to have to take derivatives of A. So we're going to need A in a small region around this point, not just at the point of interest. This would be the same if we were to calculate the electric field from the electrostatic potential. When we take the gradient of the potential, we need to know the potential in a small region. That can be an infinitesimally small region, but we still need to know it at points other than the point of interest in order to take that derivative. And so that is something we're going to have to look at. So before we go any further, let's convert this expression for A into our one-dimensional form using delta functions as we did before. Okay, so what you'll see here is that I have used this form for J in the integral here. I've missed a factor of the current, so let's put that in. It's a constant. Okay, I've got the delta function in Z should be delta function in Z prime. The delta function in Z prime appearing here. I've got the delta function in rho prime appearing here. I've got phi hat, and I've got the distance from the point of observation to the point of the contribution to A. And you'll notice that I have the three-dimensional volume element, d3r prime, in cylindrical coordinates. That is Z prime, rho prime, d rho prime, and d phi prime. And everything here is under these integral signs. So this bracketed term is hit by all these three integrals. Okay, this part of the integral just becomes 1 because it's an integral over a delta function. This part of the integral, this says replace rho prime with r, and all we're left with is an integral over d phi prime. So let's do that on the following page. Okay, so if we look at this, we've now reduced this to our one-dimensional form. Had we started from just a dl prime, a one-dimensional expression for A, we would have had dl prime vector is r d phi prime phi hat. But we've used delta functions to reduce it to this form, which is useful to do. But we could have started from the one-dimensional expression that you'll find no doubt in Griffiths. Okay, you might be tempted to think that you could calculate the vector potential just on the z-axis. Okay, so since we want the vector potential at this point only, we want the magnetic field at this point only, on the z-axis, couldn't we just calculate A at this point on the z-axis? And the answer is no, we can't. If we were to do this, we would absolutely get it wrong. We'd get the right value for the vector potential, but to calculate the magnetic field, we have to take the curl of the vector potential. That is, we have to calculate derivatives, and we're going to have to know the vector potential in a small region around this point. To make this quite explicit and quite clear, you'll notice that in this integral under d phi prime, r is a constant, and it can come outside the integral. Mod of r minus r prime, right, that's just the distance from this point down to the circumference as we move around the circle. This is a constant, and this comes outside the integral, and we would be left with the integral of phi hat d phi prime. As I integrate phi hat around this circle, clearly when I go from 0 to 2 pi, I get 0. That is, A must be 0 everywhere along the z-axis. All right, so A is a constant. If I tried to take its curl, I'd just get the wrong answer. I'd get 0 for the magnetic field, and we know that is not true. So in the next segment, we're going to write down our shopping list, if you like, or our laundry list for all the elements inside here, but we're going to have to be a little bit careful particularly about how we write down and what we calculate under the R' index. That's for the next segment.